Hello everyone. So let us continue our discussion. We are in week 10 and this is our third lecture. In the previous lecture, we studied how to model torsion. Now today, let us consider a torsion problem. So you can see we have a circular shaft here, right? And it is connected to a motor. Normally in mechanical systems, very often we get this type of arrangement, and using this shaft we can transmit power. So power transmitted through a circular shaft. That's our first topic today. Now with this motor, obviously we apply a torque, and that is connected to a bearing here. And because of this torque, the circular shaft rotates with the angular frequency, say omega. Now for this arrangement, the work done, say capital W is equal to T, the torque applied, times the angular deformation. Now once we define work done, we can also define power. Power P is equal to dW dt. Now in place of W we can write T times phi, so we'll get T times d phi dt. Now the angular frequency omega is equal to d phi dt. Omega is expressed in radian per second. So omega is equal to 2 pi f, where f is in hertz, right? Sometimes also we represent in terms of revolution per minute. So then we have 2 pi n is in RPM divided by 60. So n is in RPM. So per minute, how many revolutions we have, that we count here in n, and once we define that, we can quantify omega. So then what we have here, power is equal to 2 pi nt divided by 60. Now torque is expressed in Newton meter, in SI unit. In FPS unit it is represented by foot pound, right? And 1 foot pound is equal to 1.35582 Newton meter. And power is often represented in HP, horsepower, and 1 horsepower is equal to 550 foot pound per second. So that's the conversion factor. So if you work on SI unit, we can easily convert that into foot pound, and from there we can actually find out how much horsepower we need for this arrangement, where we have a motor that transmits the torque T. Okay, so let us first consider an example. So this is the example where we have a motor, as you can see here, So the motor transmits 100 kilowatt power to the shaft, right? And the RPM is given, it is 1200 RPM. Now let us mark. So the ends say A, then we have B here and C here. So what is given at B and C? 60 kilowatt and 40 kilowatt powers are transmitted. So at these 2 points, at B and C, we have, for example, belt arrangement. Through that we use this power generated by the motor for some mechanical actions, and the amount is given here, as you can see, 60 kilowatt and 40 kilowatt. Now the question is, compute tau max in the shaft and phi AC. So compute tau max and phi AC. That means total rotation and the maximum stress developed. And given capital G is equal to 80 GPa. So let us first draw the free body diagram. So we have A, B, C, and then say we apply TA here. Then at this point we have TB and TC. Okay. So now let us first focus on the segment AB. For this segment, capital T is equal to P by 2 pi F, because if you recall the expression of P here, it is 2 pi NT by 60. So T is equal to 2 pi N by 60 is F. So 2 pi F, which will come in the denominator. So we have P by 2 pi F. Then we can evaluate this. The power is 100 kilowatt. So 100 into 10 to the power 3 divided by 2 pi F. We can calculate F. F is equal to N divided by 60. So N is 1200 divided by 60. So we have 20. That means if you solve this, you'll get 796 Newton meter. So we get TA is equal to 796 Newton meter. Now, for this segment, we can also calculate tau AB. And the expression is, if you recall, 16T divided by pi d cube. The diameter of the shaft is, say, 75 millimeter. That is 0.075 meter. So what we get, 16 times T, which is 796 divided by, we have pi times 0.075 whole cube. And this is equal to 9.605 MPa. So we can calculate phi of AB. Phi of AB is, if you recall the expression, T times L divided by G times IP. So if we put the expression, say T is equal to 796 times length of the shaft, which is 1.5 meter. So L is equal to 1.5 meter. Times, we have 32 here. If you recall, IP is equal to pi d to the power 4 divided by 32. So in the denominator we have G times IP. So G is 80 into 10 to the power 9 times, we have pi, then d to the power 4, 0.075 to the power 4. Okay. So if you evaluate that, you'll get 0.0048 radian. So we get phi of AB is equal to 0.0048 radian. Now let us consider the segment BC, and we'll repeat the same exercise for BC, and then we'll see the total rotation for the complete shaft. So for BC, at this point we actually extract 40 kilowatt. So that is basically the power here. So T is equal to 40 into 10 to the power 3 divided by, we have 2 pi times 20. So this is equal to 318 Newton meter. That means TC is equal to 318 Newton meter. Obviously, the difference between these two, 796 and 318, is what is TB, right? So it is 478 Newton. Now, tau BC is equal to, we have 16 times 318 divided by pi, and the diameter is 0.075 to the power 3. So this is equal to 3.809 MP. Now we can calculate phi BC. Phi BC is equal to 318, that is capital T, times, say the length of BC is 1.2 meter. So this is for AB, and 1.2 meter for BC, times 32 divided by 80 is the GPA into 10 to the power 9 times pi times 0.075 whole to the power 4. And then if we solve, we get 0.0015 radian. So we get phi of BC is equal to 0.0015 radian. Therefore, phi AC is equal to phi AB plus phi BC. And the total of these two is 0.0063 radian. So that is the total rotation over the entire length of the shaft, right? So you see, we can calculate the total rotation, and we have also calculated the stress, right? In one case, for the section BC, we have 3.8 ampere, and for the section AB, we have 9.6. That completes the solution. So you have seen how we can use this relation between torque and stress and power, and can solve the power transmitted through a circular shaft that very often we encounter in mechanical systems, right? Okay, so let us take a different example. In our second example, we have a shaft made of two different circular shafts. So let us mark, say, A, B, and C. Two ends are fixed, so this is fixed, and this end is also fixed. Then at the middle, let us apply a torque of T0. Our task is to find out tau AB and tau BC. Now, if you look at the section AB and BC, say over BC we apply a torque TB. Obviously, the total torque applied over the section AB is T0 minus TB. So we have here, say TA is equal to T0 minus TB, and at this section we have TB. Now phi B is equal to TA times, say, the length of the first part is L1 and second part is L2, and G1 and G2 are the material constants. Similarly, we have IP1 and IP2. So TA times L1 divided by G1 times IP1 is the rotation for the segment AB, right? Minus TB times L2 divided by G2 times IP2. This must be equal to 0. Right? Because at the section B, we have the same amount of rotation to maintain compatibility between the two segments, right? So the angle between A to B is exactly the same what we have for B to C. And that's the reason we have this expression, right? Okay. Now, in place of TA, what we can write is T0 minus TB times L1 divided by G1 IP1 is equal to TB times L2 divided by G2 times IP2. So effectively what you get? T0 times L1 divided by G1 times IP1 is equal to, we have TB times L1 divided by G1 times IP1 plus TB times L2 divided by G2 times IP2. So what we have, T0 times L1 divided by G1 IP1 is equal to TB within bracket, first term is L1 divided by G1 IP1 plus L2 divided by G2 IP2. That means TB is equal to T0, and if you simplify this expression, we get L1 times G2 IP2 divided by, we have L1 G2 IP2 plus L2 G1 IP. So once we find out TB, we can also find out TA, which is nothing but T0 minus TB. Now if you consider a special case where we have G1 is equal to G2 is equal to G, that is the same material is used, and IP1 is equal to IP2 is equal to IP, and L is total length is obviously equal to L1 plus L2. Then what we get? We get TB is equal to T0 times L1 divided by L, and TA is equal to T0 times L2 divided by L. What it means, if we go back to the diagram again, that means the torque TA and TB, if you look at the expression, the ratio of TA by TB is equal to L2 divided by L. So they are distributed in the inverse ratio of the length if we have the same material and uniform cross sections. That means IP1 equal to IP2. So this is an important relation for a circular shaft. Now we can also find out tau AB, that was the main objective. Tau AB is equal to TA times D1 divided by twice I1. Similarly, we can also calculate tau in BC. So we have TB times D2 divided by 2 times IP2. Now, if you go back to the original problem, because we have fixed condition, for this problem we can actually, we have applied T0 is equal to TA plus TB, right? So this is equilibrium equation at the point B. Now we can also use compatibility conditions phi. If you just look at this expression, because at the point B, the rotation will be same whether we come from AB or CB. Then from this example, what we get is TA by TB is equal to L2 times G1 IP1 divided by L1 times G2 IP2. Now in this expression, if we put G1 equal to G2, so these two will get cancelled, and IP1 equal to IP2, then polar moment of inertia will also get cancelled. Effectively, we'll get L2 by L1, the same relation that we have just derived. Okay. So this is from the compatibility condition at the point B, and we can see that the same expression of TA by TB we get. So that completes the exercise. We have evaluated TA and TB, and from this expression we get phi B. Okay, fine. So now let us take a different example. So our example 3 is a composite shaft. If you recall, bending of beams, we considered a beam cross section made of, say, wood and steel, and for that we evaluated the modular ratio and the stress distribution. Now in case of torsion, let us consider a shaft made of two different material. As you can see, we have one material here, so that is material 1, and this is material 2. So we have two materials. Obviously their shear modulus are different. So we have, say, GA, GB. This one is, say, A, and the outer material is B. So GA and GB are modulus of rigidity, right? Also we have IPA and IPB. These are polar moment of inertia. Obviously the total torque that can be applied to the section is the summation of TA plus TB. And for both of them, we'll have same phi because we have to maintain the compatibility, right? So phi we know, if we start with A, so it is for material A, we have TA times, so length of the shaft is L divided by, we have GA times IP, which is equal to TB times L divided by GB times IP. Now, for the complete shaft, phi is equal to T times L divided by, we have GA IPA plus GP IPB, right? And if that is the case, we can evaluate TA is equal to T times GA IPA divided by GA IPA plus GB IPB, and TB is equal to T times, we have GB IPB divided by GA IPA plus GB. Now for both of them we can also find out shear stress. So tau A is equal to TA times RA divided by IPA, and TB is equal to capital TB is into RB divided by I. So we have the complete expression for the composite shaft. So we have the expression for TA, TB and tau A, tau B. And we have also expression for phi for the composite shaft that comes from the compatibility condition. So this is the compatibility condition. So using compatibility condition, we have evaluated the net rotation over the shaft of length capital L, right? But the shaft is made up of two different materials, and then here also we can quantify the individual torque in the material A and B, and because of that, what is the stress development. And if you recall, what is the distribution of stress? It is linear, starting from 0 at the center, and as we move away from the center, it linearly increases and having the maximum value at the surface of the shaft, right? So that is the distribution. Now with that, our discussion on circular shaft comes to an end, and we will continue with this topic. We'll see how we can introduce warping over the section. As of now, whatever we have discussed, it doesn't consider any warping. So in our next class, we will introduce you how to model warping in torsion. If you have any doubt, please drop a mail to us, then we will clear your doubt, or otherwise you can also discuss the problem in our open session. Thank you very much.